Hi ladies and gents, welcome to our very last unit in Business 306. We're taking a look at linear correlation and regression. Let's go back and take a look at where this is at in the course. Remember that everything that we've been working on has been moving towards inferential statistics with units E and H. That's really, in a sense, the end of the course, but we're just going to make a quick jump off here to Unit R. And this is just an extra at the end of the course. It was added because Mount Royal has asked that we put that in there, as well as CPA, the accounting organization. But it's actually a good place to, it's a good thing to introduce you to that, because if you don't go on to Business 307, then you've been introduced to something which is an important concept in statistics, and it's an application of inferential statistics which is very common. And so you'll often hear about regression lines. So we want to give you the basics about how to read a little bit of regression output and how to do some simple calculations. But if you go on to Business 307, we will go into this in a lot more depth. Let's go back to where we were, and we're taking a look at linear correlation and regression. So Unit R, we're going to take a look at 4 different topics here. So we'll look at Pearson's linear correlation coefficient, which is R, and the simple linear regression line, the R-squared value, and then regression output using Excel. Now let's talk about this thing called the correlation coefficient R. This is something which is similar to X bar. X bar was a sample mean. S was a sample standard deviation. P bar was a sample proportion. R is a sample correlation coefficient. And we will use that in Business 307 to test something called Rho, which is the population correlation coefficient. You don't have to worry about that in this course. We're just going to take a look at R, which is a sample measure, but it's a measure of the correlation between 2 variables. Now, an important thing about correlation is that correlation is something which is often misused by people. So I might say something like, the number of times that I go out to eat is really correlated with how hungry I am. The problem with that is that although the number of times that you go out is a quantitative variable, I would need to come up with a quantitative measure for my hunger. And then we would need to come up with a linear relationship between the two, something that we'll later call a regression line. And show, so it shows as one increases, how does the other increase or decrease. So people tend to use that word correlation rather loosely, and it's usually incorrect. It has a very specific meaning, and it's talking about the linear relationship between 2 quantitative variables. Usually they're interval in nature, although in 307 we'll also talk about how you can do that with ordinal variables. Let me show you some diagrams down here, and it will all have to do with this statement right here, that your R will take on values from -1 up to +1. So let's take a look at 5 different scenarios here. And the first one is what we call a perfect positive correlation. So let's draw a line here. And then if all of the points then are exactly on the line, I'll show them as little x's here, and that particular line has a positive slope, then we say that we have a perfect positive correlation. That is an R of +1. On the other hand, if we have all of the points on a line, kind of a jiggly line there, but all of the points are exactly on the line, but the line has a negative slope, then we say that we have a perfect negative correlation of -1. Let's take a look, though, at an r equal to 0. So these are going to be 3 examples where your r is equal to 0. Here's one, and that is if you end up with all of the points on a line, but that line is horizontal. So they might be exactly on the line, but what this is saying is that as x increases, y does nothing. It has no effect on y. So there's no linear correlation between them, or the correlation is 0. Here's another case that would give us a correlation of 0, and that is if you have just a scattering of points like this that don't have an obvious pattern to them or no obvious linear pattern to them. If you were to plot the best line that goes through those points, you couldn't do it. Is it a positive slope? Is it a negative slope? So what happens is the regression machinery, the formulas just goes blah, like that. So it gives you a horizontal line just like the one on the left there. The one next to it in the middle. And then there's one other possibility here, and that is that you could actually have a nice relationship between x and y, but it might not be linear. It could be, say, quadratic. And so in this particular case then, it's a very strong relationship that you have between them. They're all on this nice quadratic line here, but it's not a linear relationship. And so what happens is that the equations then give you, and that's not a very good one there. Let me redo that. The equations give you just a horizontal line like that. So a slope of 0 means an r of 0. So those are the possibilities. Of course, most problems fall somewhere in between. So you might have a general upward scattering of points, and so you have a positive correlation, but it's not perfect because they're not all on a line. They're scattered around a line, and so it might have a correlation of, say, positive 0.6 or something. Or alternatively, they could have a general downward trend, but they're a scattering of points, not all on a line. That would be a negative correlation. Maybe that's minus 0.7 or something like that. We'll see an example of that in this next problem. Let's take a look at how you calculate r. Just a note before we get there, and that is, it says here, an r of plus or minus 0.7 is generally indicates a strong linear relationship between x and y. But you can still have lower values of r that are still significant. Now, that will have more meaning when we get into Business 307. We're asking if they're significantly positive or negative. And you can have something that has an r of 0.1, but it's significantly positive, so it's different from 0. And that can happen with large n's. But we'll look at much smaller values in this particular case here in terms of our sample size. And so generally when you're looking at r's up around 0.7 or higher, then you'd say you've got a strong relationship. Obviously, as they get lower, you would say that they're weaker. And the closer to 0, you would say that there is not much indication that there is a relationship at all. Here is the formula that we use for that, and I know it's an ugly looking thing here, but once you've tried it a couple of times, you'll see how this works out here. And we'll talk about the formulation of this when we get into Business 307. So what I want you to notice here is that there's different kinds of sums here. The sum of x, the sum of y, the sum of the xy's, the sum of the x squares, and the sum of the y squares. And then finally there's n. Now let's take a look at each one. Let's take a look at n first. And n is actually equal to the number of pairs. That's really important to note here. So if you look at this problem down here, we'll see that we have a sample of 15 students. There's 30 numbers because each student has 2 different numbers, right? The hours, X is the hours of study per week, and then Y is the grade that they get in Stats 101. And we want to see if there's a linear correlation between them. So there's 30 numbers in total, but the important thing is that there's 15 pairs or 15 students, each with an X and a Y. Then what we're going to do is we're going to set up columns here. So we've got an X column, we've got a Y column. We're going to have an X squared column, a Y squared column, and an XY column. And all we do in each case then is you just go row by row. And so 14 squared is 196. So this particular number here, let me just change colors here. This number here then is 14 squared. This number squared. Okay? Now if we took 59 squared, then we're going to get this number here, which is 3481. And then finally, if we take 14 times 59, then we're going to get the XY value, which is 826. So that would be 14 times 59. So you do that for each row. So I'm not going to do it for every row, but let's just take a look at the second row. So 17 squared is 289. And then 72 squared is 5184. And then 17 times 72 is 1224. And you do that all the way down until you get to the bottom here. And so what I'm going to do then is to put in the sums like this. All right, so the sum of the x's turns out to be 368. And the sum of the y's is 1031. The sum of the squared x values is 9480. It's important to note that this is the sum of the squared values, not the square of the summed values. So this is not 368 squared. This is squaring each number as you go and summing them up, just like we did when we calculated variances way back in Unit C. The sum of the squared y values is 730,000 and 79. Oops. And 79. And then the sum of the xy's is 25,864. So the last thing I'm going to do here is just put in those symbols here. So this is the sum of the x's. This is the sum of the y's. This is the sum of the x squares. This is the sum of the y squares. And this is the sum of the xy's. Now, let's go and calculate the r value for that. So r is equal to, and I'm going to use this formula up here, this guy here. Let's just clean that up a little bit. All right, so the sum of the xy's, which would be 25,864 minus the sum of the x's times the sum of the y's divided by n. And remember, your n is 15 pairs, not 30 numbers. So that's the numerator. The denominator looks a little uglier, but all it is really just a variation of a square root, given some n's crossing out and so on, but it's the same concept here. So what we have here then is the square root of, the square root of the sum of the squared x's, so 9480 minus, and then 368 squared over 15, and then the square root of the y squares, so 73,079 minus 1,031 squared, again over 15. The n is always 15. And when the smoke clears on that, what you'll end up with then is a correlation value of positive 0.570. So a fairly strong positive correlation. It's we wouldn't say it's a super strong correlation, but it's fairly strong and it is positive. So as X increases, then Y increases. So we're saying that the more that you study, the higher your grade should be. Obviously, this is something which we all agree on. Well, your instructors do anyways. Let's continue on here and take a look at, on page R3 here, at the regression line. And so while the correlation coefficient R is a good measure of the strength of the linear relationship, the regression equation expresses Y, which is the dependent variable, as a linear function of X. So it looks like this here. This is the formula. Now these guys right here are called the Y hats. Statisticians are a practical bunch, and so that's what they call them, the Y hats. You can see that there's a little hat up there. And they're the points actually on the line. The actual pairings of the X and Y's will give you points that are not necessarily on the line, which we're going to see at the bottom of this page. The intercept is this guy here, B0, and then B1 is your slope. And here's the formulas that you use to calculate these guys. What you'll notice is that the formula for B1, which is the slope, is very similar to the formula for R, the correlation, and that makes sense in that a positive slope corresponds to positive correlation, and so on. Okay, so let's take a look here, down here, at the hours grades example. The first thing that we're going to do is to draw a scatter plot. Now that takes a little bit of time, so I've already gone and done that for you. And so I've got the X variable, which is hours, on the X-axis. And that's our independent variable. So we're looking at X, the number of hours, being a determinant of Y, the grade. Just as a bit of an aside here, we'll go into this more in 307 here, but it doesn't necessarily prove causation. We don't say that we're 100% sure that the number of hours actually is something that determines the grade, and unless we control all possible variables, we can't actually say that, and we can't put these kind of things in a petri dish. But we are talking about whether there is a relationship between them. Hey, just as an aside, let me give you an example of that, and that is when we're talking about, people are talking about, well, does 5G networks cause COVID? And it's kind of a goofy thing to look at there. But what they're saying here is, well, if you take a look at where COVID tends to be high, that's where the 5G networks are. And here's the thing, is that both of those actually have something else in common, and that is population density. So you tend to get higher COVID cases in the cities where there's higher density, and so there's more contact. Of course, that's where your 5G networks are. That's where they're being rolled out there. So one is not the cause of the other, even though they might actually be highly correlated in some way. I don't know what the numbers are, but that's what the conspiracy theorists are saying there. But it has to do with population density. Anyways, what we've got here then is X is the number of hours, Y is the grade, and so every one of these blue dots then represents a pairing. So for instance, if we take a look at that very first one here, which was the 14 and 59, then that would be down here, that would be, well, that would be this guy right here. Okay, so there's the first one. So these are all of the dots here then. And what you can see is that there's a general upward trend here. And that makes sense when we take a look at the measurement that we had for R, which was positive 0.57. So not super strong, but it is strong, and it's definitely different from 0. It's not a flat line, it's an upward sloping line like that. Let's do some calculations here. And so the calculation then for the slope is equal to, and again I'm going to be using these formulas at the top of this page here. So the sum of the xy's is 25,864 minus, and then we've got 368 times 1,031 over 15. And that's actually the same numerator as we had for r, if you take a look at that. And then the denominator basically is going to be just this term here, but without the square root sign. So that's going to be then 9480 minus 368 squared over 15. And that whole thing comes out to a positive slope of positive 1.262. Then we can come up with the intercept. The intercept is going to be the sum of the y's, which is 1,031 over n, 15, minus 1.262 times, what do we got? 368 was the sum of the x's over 15. And that comes to, let's put it down here, 37.770. So here's the equation for the regression line, is y hat is equal to, and I'll just take these now to 2 decimal places, 37.77 plus 1.26 times x. Or what some people do is they write it in terms of the actual variables. So we would say grades hat, our estimate of our grades, is equal to 37.77 plus 1.26 times hours spent. And that means that for every 1.26 hours that you spend studying, then your grade should go up by 1%, I guess it is in this particular case, if you take a look at the original numbers. Last thing that I want to do here is just draw in the regression line here. And so it's, now we could get pretty technical in terms of this. This is the, if you take a look at my sketch here, all it is a sketch, and so it's not exact, but we would have something that has an intercept of about, what was it, 37.7, and then you've got a positive slope like that. So something like that, it would be the regression line. So I think that's about where I want to end in this particular lesson. And let's just see if we answered all the questions for number 2. Draw a scatter plot. We did that. Remember to label your axes and then calculate your intercept and your slope, show the formula, and then sketch in the regression line. So we are done. The next one we will take a look at something called the R-squared value and reading the computer output. So we're going to stop it here.